Hello everybody, I'm Dr. Neel Kamal, Associate Professor, EEE Department, School of Engineering Technology, IIMT University Meerut. So today I'm representing my second lecture of electrical machine modules. So let us continue. So we will discuss in this lecture about voltage regulation of single phase transformer, transformer losses and its efficiency, all-day efficiency and what the condition of maximum efficiency, and then indirect loading test of transformer, in which we will discuss about the open circuit test and short circuit test of the transformer. So let us continue. First of all, what is voltage regulation? Voltage regulation is basically change in voltage magnitude between the sending and receiving end of the component. Mostly it is used in power engineering to describe the percentage voltage difference between no load and full load voltage distribution lines. As we know, we are having the transmission lines of thousands of kilometers. We are receiving end voltage and sending end voltage may be different. So what is the difference? This is known as basically the voltage regulation. And in terms of load, we can say we are having the no load terminal voltage and we are having the full load voltage, and there will be the definitely difference between them. So this difference is known as the voltage regulation. So as this voltage regulation is always represented by the percentage, so we can say voltage regulation is equal to E2 minus V2 upon V2, where E2 is the secondary side induced EMF, that is the no load voltage of secondary side, and V2 is the terminal voltage of secondary side, means the full load voltage, and in the denominator part this is also the V2, and multiply by the 100 to get the percentage voltage regulation. So we are having basically different type of voltage regulation based upon the power factor angle. So first of all, we are taking the voltage regulation in case of lagging power factor. What is the meaning of lagging power factor? Lagging power factor means the current is lagging behind the voltage by any angle that is known as the theta 2. In this figure we are looking here, just I am taking the pointer, yeah, looking here, I2 is the secondary current. In this figure you are looking here, I2 is the secondary current and it is lagging behind the terminal voltage V2 by an angle theta 2. Okay, so voltage regulation of the transformer for this lagging power factor means V2, and then we are having some voltage drops in terms of resistance and in terms of reactance, and then finally we get the induced EMF at secondary side, that is represented by E2. So in this geometrical figure we are having OD as representation of E2. So when OC and OD may be very small, then we can neglect and OD is considered nearly equal to OC. OD is nearly equal to OC, means OC we can break this value between OA, AB and BC. Look in this figure, OA, that is the terminal voltage V2, AB, we are having the current that is lagging behind by the voltage, secondary voltage V2 by the angle theta 2. So resistive voltage drop will be I2R2, that is I2R2, making then angle theta 2 with supply voltage V2. So it have the horizontal component, that is I2R2 cos phi 2, that is represented by AB, and similarly BC is just equal to EF because of the rectangular shape. BC is equivalent to EF, and what is the value of EF? We are having the reactive voltage drop I2x2 here with an angle theta 2. So its vertical component will be the EF, that is equal to I2x2 sin phi 2, and that is equal to BC. So overall we can say the value of OC will be equal to OA plus AB plus BC, and that is equal to V2, OA means V2 and AB means I2R2 and BC means I2X2 sin phi 2. Once again I am repeating, OC means OA, that is equal to V2, and AB means I2R2 cos phi 2. That is a horizontal component of I2R2, that is I2R2 cos phi 2. And BC, or we can say equivalent to EF, that is equal to I2X2 sin phi 2. So OC and OD is approximately equal. If we can say, then OC is equal to V2 plus I2R2 cos phi 2 and I2X2 sin phi 2. And what is OC? OC means E2. So shifting this V2 on this left side, then we can say E2 minus V2. E2 minus V2 will be equal to I2R2 cos phi 2 plus I2X2 sin phi 2. And when we divide this by V2, we can get the voltage regulation, that is equal to I2R2 plus I2X2 sin phi 2 divided by V2 multiply by the 100. So overall we can say the voltage regulation of transformer for lagging power factor will be equal to I2R2 cos phi 2 plus I2X2 sin phi 2 divided by V2 and multiply by 100. Okay, now voltage regulation of transformer for leading power factor. What is the meaning of leading power factor? Leading power factor means current is now leading with the supply voltage V2 by an angle that is equal to theta 2. Current is now in leading case. Looking here I2, that is I2 is leading by the voltage by theta 2. So this is leading current and the power factor is known as the leading power factor. So in this case, just like the previous case, we can say OD is representing the secondary induced EMF, that is E2, and what is V2? V2 value in this figure is represented by OA, and AB is the voltage drop at resistive part, so we can say I2R2, and it is having the horizontal component, we can say I2R2 cos phi 2. And once again, what about BC? BC and EF is same, just like in case of lagging system, BC and EF. And you know DE is the I2X2, and this DE, or we can say I2X2, have the vertical component that is equal to FE. What is the value of FE here? The value of FE here is I2X2 sin phi 2. Okay, so now OC means OA plus AB minus EF. Here OC, we have to obtain OC. The value of OC will be equal to OA means V2, and AB means I2R2 cos phi 2. But this is totally OB, but we have to obtain OC, then we have to subtract BC part. So minus BC means minus X2 I2X2 sin phi 2. So overall we get OC equal to V2 plus I2R2 cos phi 2 and minus I2X2 sin phi 2. And just like the previous case, we can say when OC is nearly equal to OD, then we can say E2 is equal to V2 plus I2R2 cos phi 2 minus I2X2 sin phi 2. And then E2 minus V2 is the voltage regulation, and it is further divided by V2 to obtain voltage regulation, that is equal to now I2R2 cos phi 2 minus I2X2 sin phi 2 divided by V2. And then finally multiply this fraction by 100 to get the percentage voltage regulation. So this is the case of leading power factor. So we already have discussed about the lagging power factor and leading power factor. Now come to the next, voltage regulation for zero power factor. Zero power factor means cos phi value is 0. So there is no difference between no load voltage and full load voltage. And when there is no difference between no load voltage and full load voltage means no voltage regulation, or we can say zero voltage regulation. So it doesn't have any meaning. So voltage regulation in this case is equal to 0, and that is not practically possible, and that is only the theoretical possible in case of for the ideal transformer, because the ideal transformer have the different terminology we are using, where we are using zero resistance or zero ohmic resistance, and no leakage flux, so such type of system. Now, and finally, voltage regulation for the transformer for unity power factor. Unity power factor means phi 2 is equal to 0. So we can say cos phi 2 is equal to 1. So in the previous equation where we get cos phi 2, we can replace phi 2 by 0. So we will get cos phi 2 is equal to 1. So this shape will appear here. I2 R2 resistive voltage drop, because cos phi is equal to 0. I2 X2 means just a right angle triangle shape. So unity voltage regulation indicate there is no phase difference in the second terminal voltage and secondary current. Now, for obtaining the efficiency, first of all we must know about the different type of losses of transformer. So how many type of losses are there? There are basically two type of losses. One is known as the iron losses, and second is known as the copper losses. Iron losses is further divided into two parts. One is known as the eddy current losses, and second is known as the hysteresis losses. And copper loss is the variable losses, and these generate heat in the transformer. Now, I square losses, I square R losses, or we can say copper losses or variable losses. These losses occurs in both primary and secondary side due to the current and ohmic resistance, and therefore these are known as the I square R losses. And these losses translate heat and are often referred copper losses, basically because winding is almost made of copper, so that is known as the copper losses. And second, losses due to the core of the transformer, so this is known as the core losses. So there are two type of core losses, hysteresis losses and eddy current losses in the steel core, and these losses are constant by nature, so these are also known as the constant losses. Iron losses, core losses and constant losses all are same. And variable losses, copper losses and ohmic losses are known as the variable losses, or and almost we referred as copper losses. Now about the transformer efficiency. Transformer efficiency we can define as the ratio of the output power to the input power. Output power we are representing here P out, and input power we are representing here P input, and multiply by 100 to get in percentage. What the difference between the input power and output power? The difference in input power and output power is the power losses. So obviously if we add the power losses to the output power, we will get the input power. So the formula now we can say for efficiency, P output upon P output plus P losses multiply by 100. And P losses means two type of losses we are considering here. One is known as the copper losses, that is representing by I square R losses, and second is the core losses. So therefore overall the formula for transform efficiency we can use here Vs Is cos phi upon PCU plus P core plus Vs Is cos phi x means multiply by 100. S stand for secondary side, because we have to obtain the output side. Output means secondary side. PCU means copper loss, and P core means iron loss or constant losses. So in the continuation, condition for maximum efficiency of transformer, when will be the efficiency of the transformer will be maximum value. So P output we are representing here V2 I2 cos phi 2, and copper loss we are representing here I2 square R02. R02 means secondary side ohmic resistance and I2 is the secondary side current. So what about the total losses? Because iron losses always known as the constant losses, so we can add is as it is Pi, that is iron losses, and PCU means copper losses, that is equal to I2 square R02. We are writing here I2 square 02 because here secondary current is variable by nature. So efficiency now we can represent as V2 I2 cos phi 2 upon V2 I2 cos phi 2 plus Pi plus I2 square R02. If we divide this by I2, this fraction by I2, numerator and denominator, if we divide by I2, what will we get? We get V2 cos phi 2 upon V2 cos phi 2 plus Pi upon I2 plus I2 square I2 R02. Next, so to obtain maximum value of efficiency, denominator should be minimum. In the previous slide, we have a fraction V2 cos phi 2 upon V2 cos phi 2 plus Pi upon I2 plus I2 R02. So this denominator part that is V2 cos phi 2 plus Pi upon I2 plus I2 R02. The derivation of this with respect to variable current, that is I2, must be equal to 0 to get the maximum value of this efficiency. So V2 cos phi 2 means constant, so derivation of this will be 0, and Pi upon I2 means derivation of this minus Pi upon I2 square, and derivation of I2 R02 with respect to I2 is R02, that is equal to 0. So by this equation we can get Pi is equal to I2 square R02. So Pi means constant losses, I2 square R02 means variable losses. So when constant losses is just equal to the variable losses, we can say transformer will be at maximum efficiency. Transformer will show the maximum efficiency when constant losses are equal to variable losses. What the all day efficiency? In the previous case, we are discussing about the efficiency in which we are observing that we are taking only the power into consideration. But suppose the transformer that is working for 24 hours. So 24 hour means we are considering the time also. Instead of power, now we are considering the energy in this case, because the multiplication of power with time, we will get the energy. So such type of efficiency in which we are using the energy in output for 24 hour and energy in kilowatt hour for 24 hour, then this type of efficiency is known as the all day efficiency. So all day efficiency is generally using for the distribution transformer, because distribution transformers are used for 24 hours. Once these are commissioned on a pole, they are working for all 24 hours. So this type of efficiency will be considered here. Now a brief quiz. Which loss is the variable loss of the transformer? So which loss is variable? Copper loss. Iron loss always remain constant, and copper loss depend upon the load current, value of load current, that is variable by nature. So we can say copper losses are variable. Second question, transformer rating are usually expressed in. So transformer rating we generally express in volt ampere or kilovolt ampere. For the mega power system we are using MVA, mega volt ampere system. Instead of kilowatt we are using here volt ampere or kilovolt ampere system, because transformer basically depend upon iron losses and copper losses, because a good transformer is this type of device that have minimum heat producing system, because copper loss are variable by losses and depend upon the ohmic value of resistance. So these type of power law of I square R loss will produce heat. So these two losses, in which copper loss depend upon the current and iron loss basically depend upon the voltage. So the multiplication of this voltage and current, due to which we are having the transformer rating in terms of volt ampere system. Now what is the condition of maximum efficiency? So we know the for the maximum efficiency the two type of losses, that is iron loss and copper loss, both losses should be equal. At this stage we will get the maximum efficiency of the transformer. Just a numerical quiz question: if we are having the full load copper loss 200 watt, half load of copper loss will be equal to what? So we are having I square R. I square means we are having the square term of current here. So copper loss will also having this fraction x square I square R. X is a fraction which represents the load. Half load means x is equal to 1 upon 2. Half load, x is equal to 1 upon 2. Means we are having now copper losses divided by 4. So 200 divided by 4 means 50 watt. So if we have the full load 200 watt, half load or copper loss will be 50 watt. Open circuit test. Open circuit test is carried out by connecting low voltage side as primary side and high voltage side at the secondary side, and ammeter, voltmeter and wattmeter will be connected on the low voltage side, and we are having the variac, or we can say auto transformer, for supplying this primary side. So we will have the value of these instruments. Ammeter means no load current, voltmeter to get the voltage, and wattmeter for the power used in this system. In this we know no load current is having very small value, so there is comparatively very small copper losses that can be neglected. And secondary side, we know as per the name suggests, open circuit test means we have not connected load here, means there is no secondary current on this side, means I2 is equal to 0, means there is no copper loss on the secondary side. The copper losses will occur only the primary side, but comparatively these are very small. So this wattmeter will represent the entire iron loss of the system. And for the different calculations, we are having the power factor cos phi W0 upon V0 I0, where W is the 0 is the wattmeter reading and V0 is the voltmeter reading and I0 is the no load current. This no load current having the two component, one is the magnetizing component, that is IM, that is equal to I0 sin phi 0 as per the previous slides, and core loss component have I0 cos phi 0, and magnetizing branch reactance X0 is equal to V0 upon IM, and resistive representative core R0, that is equal to V0 upon I0. Now short circuit test. Short circuit test will be obtained by connecting all these voltmeter, ammeter and wattmeter on the high voltage side, and secondary side, or we can say low voltage side, will be short circuited here. So there will be the flow of short circuit current in this system, and very reduced voltage will be applied on this primary side, hardly 2 to 5% of this full rated value. So wattmeter will represent the short circuit power, or we can say full load copper losses, and different values of this side parameters means R01 means short circuit wattage upon short circuit current square, and impedance will be equal to VSC upon ISC. VSC means short circuit current and ISC means short circuit current. VSC means short circuit voltage. And how we can get the reactive part, that is impedance square minus resistance square and then under root, we will get the reactive part. And cos phi FC means WSC upon VSC multiplied by ISC. We will get the different parametric values in case of short circuit system. So thank you very much looking this video, and we have discussed in this lecture about the voltage regulation, efficiency and condition of maximum efficiency, and then finally indirect loading test of transformer, in which we have discussed about the open circuit test and short circuit test of single phase transformer. So see you in the next lecture. Thank you.